Speakers Zach Murphree with VELO3D and Andrew Carter from Stratasys Direct.
Good morning. Can you hear me out there? Excellent. I'm really excited to be here today with Andrew Carter to talk to you guys a little bit about VELO3D and our products, specifically the capabilities of our products to ease the transition to large-scale serial production. I really appreciate the introduction from Pete Zielinski this morning to the session because I think it helps to put everything into context around kind of the transition period that we're in Metal AM and going really from the rapid prototyping type of mentality into serial production. And especially to be following GE, one of the pioneers in actually getting parts into production. And I think if you look at the GE story, one of the things that you'll see is that it's not necessarily an easy road to take to get parts into production. So VELO3D is really working hard to build a system that makes that transition much easier so that it's something that's a little bit more accessible to everybody. So when we look at some of the things that hold metal additive manufacturing back from becoming a really good solution for serial production, we identify two main issues. The first of these issues is a geometric limitation. And that's really, if you look at the lanyard that you have on, we have the 45-degree rule. That's what we're referencing. And so with a laser powder bed system, in general, if you're printing surfaces that are below 45 degrees, they require supports. And supports oftentimes can make a part uneconomical or simply impossible to print in a way that's good for serial production. The second is part quality. And I think one thing that's important to note here is that all of the different modes of metal additive manufacturing are capable of producing very high quality parts. That's not something that we refute at all. I think the real challenge is that for any specific part that you pull off of a metal additive manufacturing system, knowing whether or not that part is good can be challenging. And that confidence is really what's required to be in a series production environment. So VELO3D is approaching these two problems, along with many others, as we try to help accelerate the adoption of Metal AM for series production. On the geometric freedom side, we've worked pretty hard to develop processes that are capable of printing geometries that other more conventional Metal AM systems aren't capable of printing. So we are truly trying to break this 45-degree rule. And with the Velo Sapphire and our flow software, you'd be able to print geometries that have angles well below 45 degrees, down below 10 degrees in a lot of cases. And now we're even capable of printing some fairly large horizontal overhangs without any support structure. So it really opens up the application space and the parts that might be considered as potential candidates for Metal AM. On the quality side, we've built the system from the ground up to be a production-focused system. And one of the things that came from our process development, where we tried to push the limitations of what Metal AM can do, is that we needed to operate in a much smaller process window. And we had to develop metrology on the system to make sure that we're able to operate in this process window. So the system is really advanced in terms of the metrology that's actually on board the machine and the software that we use to both prepare the prints and then to present the data after the print is complete. The machine itself is called the Velo Sapphire. It's a laser powder bed fusion system. Our build plate is a round build plate, which is a little bit different than what you might see on a lot of other systems. It's a 315 millimeter diameter, so a little over 12 inches in diameter, 400 millimeter in Z, and that's the actual build volume. So you can build a part that's a 400 millimeter or 16-inch tall part on the system. It's equipped with two 1 kilowatt lasers. So it's quite a bit of power, a lot of melting power on the system. We're currently running Inconel 718 and Ti 6.4, although we do have a couple of other alloys that are in development and will be announced soon. But for this conversation, I think the thing that we're trying to focus on is the metrology suite. And it really is the different sensors and metrics that we've built into the system that allow it to basically give the user a complete confidence in their part at the end of the day. One of the things that I think is often overlooked in metal AM systems and in the installation and getting a system up and running is what happens before the machine ships. So our company has quite a bit of pedigree from the semiconductor capital equipment manufacturing. And one of the things that happens, especially companies like Intel, is that they have a copy exactly mentality. And that means that any machine that's installed at some place like Intel has to be able to produce the exact same outcome when given the same set of inputs. And that's one of the things that we're really striving to do with our system, with the architecture of the system and the metrology that's built in. But the factory acceptance test is where this all starts. So our factory acceptance test is a very thorough test of the entire build volume of the machine, testing for the surface roughness, dimensional accuracy, a full suite of mechanical property testing, the throughput of the system, and a number of other metrics. And these are all compiled and then repeated once the system's installed on site. So this helps us to know, even before we begin kind of with the calibration and certification of the equipment, that the machine is performing nominally to our spec. Once the system's installed, it's also very important to be able to maintain this calibration and the confidence in the parts that are being printed. I think another thing that's very challenging with metal AM equipment as it currently stands is that a lot of the calibrations are performed on essentially a PM schedule. So every 3 to 6 months, you'll have a tech come in and they'll perform calibrations, and at the end of that, you'll know my system is in spec. But in the interval between those PMs, it's not necessarily clear that the system is nominal. So when you're starting a print, how do you know that the system is good? Velo's added quite a bit of software capability into the system that allows you as the user to perform a pre-build calibration. So this is a single button click that before every build basically runs through the optical system and makes sure that everything is performing nominally and in spec, and then has documentation and traceability about that calibration. So this is something that's performed every single build. So you know that when you hit print, the system is in a very good condition. The other thing that's really important is that during the build, you need to have very good control over the same optics, as a good example. So we have systems built into our machine that allow the system, I should say, to measure and calibrate the overlay between the lasers on a layer by layer basis. And when you're building big parts with multiple lasers, one of the things that's very challenging is maintaining the overlay between the lasers so that you don't get a witness line, which can be something that can disqualify a part from being accepted. So with our system, we're able to do this on a layer by layer basis. And if you come by our booth over here, you can see some of the larger parts that we built with multiple lasers, and there's absolutely no witness line because we're able to maintain that calibration so well with our in-situ calibration. We're also doing some pretty detailed measurement of the powder bed. So we have a full quantitative scan of the powder bed before and after every recoat. This allows us to know whether or not the parts are behaving during the build, but it also gives us a really good sense of the powder bed quality after every recoat. And in addition to the optics, the powder bed is the other critical factor in knowing that you're going to get good mechanical properties from your part at the end of the day. With all this metrology, we also have built a reporting system that gives the user a build report at the end of the print that is essentially a machine-generated certificate of conformance. So it's a full documentation of the pre-build calibration and the health of the system when it started a print. And it also is a complete documentation of the execution of the print. And this is something that if you're a contract manufacturer, you can give to a customer, and it's a very high-value document. Or if you're an end customer, this is something that you can receive from your contract manufacturer, from your in-house manufacturing, that lets you know that the print was performed as it should have been. As we move into a little bit more discussion on the software side, I think one of the things that we were really happy to see, and a trend that we're very much on board with, is the death of the STL. So the STL as a file format is something that we think is inadequate when it comes to making very high quality parts. And we were excited to see this quote from Tim Simpson at Penn State regarding the STL and kind of the shortcomings of the STL as a file format for 3D printing. We absolutely believe in that, and we've developed our print preparation software to be a much more intuitive workflow based on CAD inputs. And when I say intuitive workflow, one of the things that I love about this software is that it's intuitive in a way that only a mechanical engineer can appreciate. It's essentially taking a machine drawing type of interaction and doing it in 3 dimensions. So what I mean by this is you can take the CAD and pick individual surfaces of a CAD model and designate them as something that needs a high quality surface finish, something that needs just throughput, so you don't really care about the surface finish. And a good example of this would be like on a stator or an impeller. So on the airfoils and on the sections that are touching the flow, you want a very good surface finish. You can designate those as high quality surface. And then on the outer housing or on a hub or on a mating surface, you can say, I don't care about the surface on this. And when the system goes through and slices and hatches the part, it actually adjusts the process accordingly so that what you get out at the end of the day is optimized for both throughput and quality, and gives you kind of the design intent of the part at the end of the day. In addition to the print preparation software, as I said before, we're also working very hard on the build reporting and making sure that the certificate of conformance that's generated by the system is something that's acceptable and really helps to give the end user of the part complete confidence in the part as it comes out of the system. So this is a little bit about the products that we're offering. We have Andrew here who has firsthand experience with the system as one of our customers. So I'll hand it over to him.
Thank you, Zach. Again, I'm Andrew Carter. I'll be stepping in for Eric Muchler today. He couldn't be here to join us. So I'm a process and manufacturing engineer for Stratasys Direct Manufacturing. Stratasys Direct is a contract manufacturer, a service bureau that houses essentially all commercially available additive technologies and processes. I support the metals process for Stratasys Direct, which comprises of 18 laser-based metal powder bed systems. But on top of that, we also house the necessary secondary operations, including CNC and quality inspection equipment, to not only machine the additive products to engineering tolerances, but also inspect and verify that those tolerances are met. Now, before I jump into the impact of quality in production, and specifically our experience with Velo Sapphire system at Stratasys Direct, I kind of wanted to provide a history of the relationship between Stratasys Direct and Velo. The two companies started talking about a commercialized production system in early 2018. And after a couple visits to Velo to assess the machine and its capabilities, a couple visits to SDM to negotiate terms and conditions and machine performance, Stratasys Direct ultimately signed on the dotted line right around the turn of the year, solidifying their spot in queue for the production system. In March, Stratasys Direct was notified that we could come witness the factory acceptance test. The next 2 weeks, the machine was packaged up and shipped to Stratasys Direct, where we repeated those series of tests in the site acceptance test. That comprised of about a week. The following week was then geared towards training. And after that week, we entered the system alongside our other systems and made it a viable machine for producing revenue-generating components, which it's been doing since May. Now, there's a lot of interest around Velo and their Sapphire system, and rather curiosity. I see the excitement not only from our customer base, but also internally within SDM. Now, our project engineers and our sales team has a system that is much like incumbent systems, but has a much wider capability. We are now offering new tools and new solutions to applications out in industry. We are routinely printing surfaces down to 15 degrees from horizontal without issue and without supports, and that geometry is not shifting as it would in other incumbent systems. Additionally, the surface finish is much more consistent. I'm not going to say it's improved, but it's much more consistent, regardless of the surface angle to the plate, angle to the recoder, or orientation to the shielding gas. The surface finish is much more consistent across the entire parts. And although the machine is expensive, nearly 2 to 2.5 times that of maybe a single laser mid-frame machine, the deposition rates are much higher. We're seeing in some cases that we can actually get the build time so far down to reduce or be lower than the incumbent systems. Now, the applications that we've seen come across our desk through our machine and actively quoting are similar to geometries that we've seen and tried to produce on our other systems, but now we're able to tackle much more complex geometries that have an order of magnitude more complexity. And thanks for the reduced need of supports, not only is less time dedicated to building the supports, but less time is needed to finish those components. Now, a lot of these geometries that we're producing now would have been no-coded due to the fact that supports would be required inside the geometry and ultimately be trapped, negating the design intent, or the features have been small enough that would ultimately be essentially damaged in the support removal or finishing operation. And these components include everything from small to rather large shrouded impellers, reaching north of 10 inches in diameter, to heat exchangers, and a significant amount of rocket propulsion components. And these components require thin walls to be built, down in the order of 15 to 30 thousandths thick, start at the extremities of the build plate, and then propagate up, unsupported, north of 10 inches. Now, bringing on a system onto the manufacturing floor, regardless of how familiar you are with the technology or the process, it is never trivial, it's never easy. And I'll be the first to admit there's been some serious lessons learned, some that we foresaw and some that we didn't. And the first one, Zach mentioned a little bit early on, and that's the elimination of STLs. This has been a great exercise for Stratasys Direct to talk about what a world would look like without STLs. And this causes complexities with our business systems because everything from quoting components to work order generation to quality inspection planning is centered around STLs. And eliminating that has really caused a little bit of a bottleneck in our business systems. But we believe that's the more robust process because we eliminate the rather archaic step of converting a native CAD solid model into a tessellated surface model. I routinely have to coach our programmers, our build technicians, that the robust support structures that they've become to know and rather overutilize aren't necessary in this process flow. It's also been a learning curve for those programmers and individuals that are really reliant on Magics and not a CAD package, because now you need to use a little bit of a summation of a native CAD modeling and Velo flow to fully make the component ready for the additive process. And those that are really accustomed to Magics, where it's a click, drag, pull, really a super souped up version of paint, it's hard to transition into the native CAD mindset. But we believe this is more robust because now any alterations to the customer CAD geometry to make it processable and buildable are now captured in the feature tree, both in, say, SolidWorks and Velo flow. Now, on the shop floor, operations that would require perhaps a maintenance technician and sometimes even equipment manufacturer's FSE are a one-click button. The machine tests itself, validates the check, and when necessary, offers up a correction and proves out that correction. And for a lack of better terms, that really boils down to laser power, laser focus, and scanner calibration. One hard lesson to learn, and that we're still trying to tackle, is the process data that's generated from the Velo flow and Sapphire process. Not only are the build files themselves very large, now taking sometimes hours, maybe overnight, to generate, but the process itself records a significant amount of process data. For a 5,000 layer build, we're looking at sometimes in excess of 1 terabyte of data. And we're coming together to determine what is necessary to retain in terms of complying to our various quality certifications, but also retain enough information to provide any retroactive root cause analysis. And this is a perfect segue into the last section that I wanted to talk about, and that's what Velo and SDM or Stratasys Direct are doing to really promote the confidence in the additive process. And this is to do post-analysis, or really analysis on the metrology data to predict bulk material properties of the deposited structure. Velo has come forward with great correlations of the bulk percentage porosity to actual measured results via radiography and and cut-up metallography. And the objective here is to increase confidence in the process, reduce the need of cut-up metallography on the components that can be a large sum of a production program in terms of costs. In addition to that, it will give the user, myself, essentially real-time data on how the process and machine, possible fleet of machines, is behaving. We volunteered to be a site validation for this added feature, and we've been producing components ongoing since about the middle of July, and will continue to do so before this product is released in Q4. So I hope this has provided some insight, not only into VELO3D and their approach to additive metals, but also into the status of Stratasys Direct and their state at onboarding the Sapphire tool. So thank you.